Hi, girls. Okay, what we're doing, for those that aren't here, 7 of you, Circle Theorem 3 that we did yesterday, I'm going to prove that a little bit later, but this is what Circle Theorem 3 was, that the angle at the centre is double the size or twice the size as the angle at the circumference. That was Circle Theorem 3. We're now looking at Circle Theorem 4, and it's related to Circle Theorem 3. So if we actually make this angle here at the centre 180 degrees, then we notice that the angle at the circumference is 90 degrees. So this is a sort of a modified version of angle at the centre is twice angle at the circumference. But if this angle here in the middle is 180 degrees and it passes through the centre, then CE is a diameter, and we notice that the angle at the circumference is 90. So circle theorem number 4 is the angle in a semicircle is a right angle. So if you can write that in your small booklet. I'll pause. Okay, girls, this is circle theorem number 5. We're going to do all the proofs at the end of looking at all the theorems. Circle theorem number 5, if you can take out your small booklet. And there are 2 parts to this theorem. The first one, so in that circle theorem number 5, we're actually going to do 2 different theorems. They're very, very similar. The first theorem relates to the second diagram on your sheet. And the theorem is angles in the same segment of a circle are equal. Now, what that means is, if you see the chord CE, that cuts off the circle into 2 segments. We've got the minor segment down here where my cursor is, and then we've got the major segment all in here. So what we mean by angles in the same segment, see this chord CE, you can form several angles. We've got angles CDE, we've got angles CFE, and angles CGE. Now they are all the same size. I'm going to move these points around. The reason they're all the same size is that they're all subtended by the same chord CE. Okay? The thing is, they are all in the reason it's called angles in the same segment is all those angles are formed in the major segment. Now, if I drag this point G down to the minor segment, notice it's not 38 anymore, it's 142. So that angle in the minor segment is not the same size as the angle in that major segment. Now, if I move point E a bit, you might see that a bit better. I'm trying to get a whole number. It's just not going to happen. So all those angles in the major segment are 51.7. If I bring one of the angles to the minor segment, notice it's 128.3. I think they're complementary, aren't they? Yeah. Okay, so that's why it's called angles in the same segment of a circle are equal. Okay, now different wording. So I want you to write that first theorem down and this different wording. Now this theorem actually relates to the bottom diagram. So don't maybe, have you started writing? If you have, just stop. Can you write it underneath the lines? Because it relates to the second diagram. It doesn't matter. It doesn't matter. What you can do is call it number 1. And same arc, same segment, there's 2 diagrams. The same arc, same segment diagram relates to this first part 1. So here, in that diagram on your sheet that says same arc, same segment, you'll put 2 little thetas up where those angles are formed. Can you see the one I've drawn up there? Sorry, people in the video, you can't see what I'm talking about. So this is same arc, same segment. Second diagram, it's saying that angle equals that angle up the top.
Is that the first one?
Yes. No, it's the second diagram on the sheet. For circle theorem 5, the second diagram, same arc, same segment. See how I've got different wording, same arc, same segment?
So the different wording one is for the second.
No, all of it's for the second diagram. Angles, all of it's for the second diagram. So please write this one underneath the lines. Don't do it on the lines. So I want you to write, because you'll understand in a minute. So angles in the same segment of a circle are equal. Different wording. Angles at the circumference subtended by the same arc or chord are equal. I know we've got a chord for this question, but it would be the same as if it was subtended by the arc CE. Okay, so it could be subtended by chord CE, or those angles are subtended by arc CE. So, yes.
Question.
Yeah.
See how like the three in the major segment, they're all the same?
Yes.
But what happens if you put all three of them in the minor segment?
They'll all be the same.
Oh, okay.
So if all three go to the minor segment,
In the same segment,
yes,
the same.
as long as they're in the, and that's why it's also called angles in the same segment. So that was a good question there by Kiara. Okay, if I put all those angles in the minor segment, they're all 128.3. So hence the theorem, angles in the same segment of a circle are equal. But obviously if they're standing on the same chord or arc. Okay? Okay, once you've written that down, we're going to look at Circle Theorem 5 Part 2, which is equal arcs and equal segments. Okay, girls, this is Circle Theorem 5 Part 2. This theorem relates to the top diagram that says equal arcs, equal chords. Actually, in your diagram it says equal arcs, equal segments, but that's fine. So with this one, instead of two angles standing on the same chord or arc, so for example, we've got chord or arc CE, we've got this blue angle, which is 32 degrees, subtended by that chord. Now, in Circle Theorem 5 Part 1, we had three angles coming off that same chord. Now, if I draw another chord in that circle that is also length 6, that has a length of 6, you'll see that the angle, my decimal, I've got to get it exactly right. Anyway, that's close enough. Okay, so I've made chord HI also a length of 6. Notice that the angle at the circumference is also 32, just like the angle at the circumference subtended by chord CE is also 32. Now I can drag HI and sit it exactly on top of CE, but that would then be sitting on the same chord. These chords CE and HI have equal length, therefore the angles subtended at the circumference by equal chords are equal.
So it means like if
This is Gloria Chan asking a question. Go, Gloria.
if they give us a question like this in the exam, they would have the length, right?
No, in an exam they might just have equal markings on them or lengths, yeah. But it tends to have just equal markings on them.
Tell us it's equal.
Yeah, they'll tell you. They might say CE equals HI, okay? Or chord CE equals chord HI, or arc CE equals arc HI. And they would actually call it the minor arc CE because there are two ways to get from CE. You can take the short distance from C to E, or you can take the long distance around the circle from C to E. So there are two arcs CE, the minor arc and the major arc. But here we're talking about the minor arc, okay? All right, so this theorem is, and this goes on the lines under Circle Theorem 5, that angles at the circumference subtended by, sorry, I've made a little mistake, subtended by equal, not the equal arcs, subtended by equal arcs, so I'm just fixing that. So angles at the circumference subtended by equal arcs or chords are equal. Okay? Girls, we're going to prove these now, so I'm going to pause this video and we're going to set up the recording on the board. Okay, girls, change of plans here. We've decided there's been a vote and everyone wants to keep doing the next three theorems, so we're doing Circle Theorem 6. So please turn over the page to the Theorem 6. We're going to prove them later. Okay, Circle Theorem 6 states, so get out your little booklet and write the theorem. A perpendicular line from the centre of a circle to a chord bisects the chord. Now, let's look at this red chord DE. What I did in GeoGebra, this program, I drew a perpendicular line from O to that chord DE. And what we found was, this is a right angle. I can't get a right angle symbol on this program for some reason. So this chord OM is perpendicular to, this line OM is perpendicular to chord DE. But what we find, if that line is perpendicular, then it actually bisects the chord M. So M is actually the midpoint. Okay, so if I can work out the distance from M to E and M to D, and I'm going to do that now if I can work out how to do it. So, oops. Yes, so I'm clicking this distance icon and I click on M and I click on E, and look, ME is 3.7. I'm going to do the same here as well. I'm going to click on D and I'm going to click on M, and that distance is also 3.7. So this line is perpendicular to the chord DE, and notice it's actually bisected the chord because the distance from there to there is 3.7. Now, if I start dragging the positions of D or E, I don't know if it's, or didn't want that. Okay, I'm going to try and, it's not going to let me drag it. It won't let me do it. Maybe this one will drag. Oh, it's not selected. There we go. So what I'm going to do, I'm dragging this chord here. Watch. I'm dragging the position of B. Notice as I drag it and the chord gets longer, I have programmed this. This line here is programmed to be perpendicular to the chord. So if we look at chord AB, OC is always perpendicular to it. It's 90 degrees. But notice if I move it and make the chord AB bigger, that C is still the midpoint of AB. Okay? So the theorem is, so what I need you to draw on your circle theorem number 6 booklet, can you please put a right angle here, I'm just indicating it here, a right angle there on your diagram, and can you put equal markings just where I'm showing you now? I want a dash there where the 4.7 is and a dash here. Do not put numbers on your diagrams. I just want a right angle there, and then I want a dash here and a dash there. Once you've done that, you can also write out the converse theorem, which is, the circle theorem 6 is if this line is perpendicular and it's drawn from the center of the chord, center of the circle to the chord, it will bisect the chord. The converse theorem is if you draw a line from the center and it happens to bisect the chord, then the angle will be a right angle. In other words, that line is perpendicular to the chord. So remember with converse theorem, you say the sentence in the reverse way. So the first theorem is if the line is perpendicular to the chord, it bisects the chord. The converse is if the line from the center to the chord bisects the chord, then that line is also perpendicular to the chord. Okay, girls, if you can write in the theorem and the converse theorem, please. Okay, girls, circle theorem number 7. And the theorem is that equal chords are equidistant from the center of the circle. Now, we've got two chords here, chord DE and chord AB. At the moment, chord AB is 9.2 and chord DE is 11.1. I've also measured the distances from O to C, which is from O to the midpoint of the chord, and it's at right angles to it, and that distance is 5.6. Notice that the distance from O to C is different to the distance from O to M. That's because the chords aren't equal. So if I make those chords equal, so I'm going to make chord DE also equal to 9.2, and once it is equal to 9.2, now the distance from the center of the circle to the chord for both of those chords is equal. They're both 5.6. Now, when you want to measure the distance of a dot to a line or a point to a line, it has to be the perpendicular distance because it's the shortest distance. For example, if I draw a line from O to, say, somewhere over here between D and M, that's not the shortest distance from O to the line. The shortest distance from O to the line is from O straight to M. It's got to be the perpendicular distance from O to the chord DE. Now remember from circle theorem number 6 that will be a right angle there. Perpendicular line drawn to a chord bisects the chord. All right, so it'll pass through the center. I haven't marked the distance of DM and ME on this diagram. We're just interested that equal chords, if the two chords are equal, then they are equal distance from the center of the circle. We okay with that? Okay, so please write that down. Circle theorem 7, equal chords are equidistant from the center of the circle, and the converse is that chords that are equidistant from the center of the circle are equal. Okay, so it's saying it in reverse. So if OM equals OC, then chord DE equals AB. That is the converse theorem.